In this video, we'll discuss rearrangements of infinite series. To set the stage, we'll start with a few definitions. If the series of absolute values of a sub n converges, then we say that the series a sub n converges absolutely. And if the series of absolute values diverges, but the normal series still converges, then we say that it converges conditionally. Using these two new definitions, we describe the behavior of the alternating harmonic series as conditionally convergent, whereas something like the geometric series sum n equals 0 to infinity of 1/2 to the n would be absolutely convergent. Informally, we can think of a rearrangement of a series as adding the terms in a different order, so the alternating harmonic series might be rearranged to 1 plus a third minus a half, plus a fifth plus a seventh minus a fourth, etc. But it couldn't be rearranged to 1 plus a third minus a fourth, plus a fifth plus a seventh minus an eighth, because this series doesn't have all the terms from the original. It also couldn't be rearranged to something like -1 plus a half, minus a third plus a fourth, minus a fifth, etc. Because this is just a different series. This has different terms. I've changed the signs of the terms. Let's define a rearrangement more formally. Let the sum n equals 1 to infinity of an be a series. A series sum n equals 1 to infinity of bn is called a rearrangement of the series an. If there exists a bijective function f from the naturals to themselves, such that an is equal to b sub f of n for all n in the naturals. And we'll certainly discuss bijections more later on, but a bijective function is one that's both one-to-one and onto, sometimes called injective and surjective. One-to-one or injective, meaning that each output only has one input mapped to it. Formally, if f of x1 equals f of x2, then x1 equals x2. And onto or surjective, meaning that each element of the codomain is actually achieved by the function for some input. So for any y in the codomain, there exists an x in the domain such that f of x equals y. Equivalently, you could think of this as the range and the codomain of f being the same set. These two conditions taken together, the condition of being a bijection, is also equivalent to the function having an inverse. So returning to the definition of rearrangement, our statement that a sub n is equal to b sub f of n formally specifies that all of the terms in the original series must show up in the new series, and they must show up exactly once. With these definitions in place, we can state our main theorem regarding rearrangements. If a series converges absolutely, then any rearrangement of that series converges to the same limit. For the proof, assume we have a series an converging to a, and let the series bn be a rearrangement of that series. Let Sn represent the nth partial sum of the series an, and let Tn represent the nth partial sum of the series Bn. We need to demonstrate that the series Bn converges to A, which is equivalent to showing that the sequence of partial sums Tn converges to A. Let epsilon be greater than 0. We ultimately need to show that the absolute value of T sub n minus A is less than epsilon for all n greater than or equal to some specific index. We'll argue that these two are close together by arguing that T sub n can be made arbitrarily close to some partial sum s sub something, and that those partial sums s sub something can be made arbitrarily close to the limit a. And since we want the whole thing to be less than epsilon and we have these two parts, we're going to make each of those parts less than epsilon over 2. Let's do that second part first. We want the partial sums s sub n to be close to a. So we can say, since s sub n converges to a, there exists a big N1 in the naturals, such that the absolute value of s sub n minus a is less than epsilon over 2 for all n greater than or equal to big N1. And now we want to bound on the difference between a partial sum of one series and the other series, but we don't know exactly which terms will show up in this difference because the terms can appear in different order. They can be rearrangements of one another. Since the series of absolute values of an converges by the Cauchy criterion for series, there exists big N2 in the naturals, such that for all n greater than m greater than or equal to big N2, the sum absolute value of am plus 1 plus the absolute value of am plus 2 plus ... plus the absolute value of an is less than epsilon over 2. And we'll be able to force all of the terms that remain in the difference between our s partial sum and our t partial sum to show up in some expression of this form, and so their combination will be less than or equal to this value, which is less than epsilon over 2. Let's let big N represent the maximum of big N1 and big N2. Now, since we want these conditions to hold, we only want to deal with terms from our sequence a sub n whose index is greater than or equal to big N. But if we just require an index, say little n greater than or equal to big N, That wouldn't be sufficient because then b sub little n could be equal to a term a sub something less than big N. So we have to account for the fact that the b terms are all out of order. We want to go far enough out in the b sequence such that we pass all of the terms that are at the start of the a sequence. Let's let f represent the reindexing function such that an equals b sub f of n. So for example, if f of 3 was 10, then the a3 term would be the b10 term. In other words, whatever term was third in the a sequence would show up 10th in the b sequence. So if our big N was 4, we would need to avoid the term a3, and so we'd need to take terms from the b sequence that had an index beyond 10. Let's let big M be the maximum of f of n such that n is less than or equal to big N. This big M is a cutoff beyond which we know all the b terms must correspond to a terms with index at least big N. And now we'll finally be able to bound that difference between a t partial sum and an s partial sum. For an index little n greater than or equal to big M, we can look specifically at the absolute value of the difference t sub n minus s sub big N, and argue that this has to be less than epsilon over 2. We've chosen that sum tn such that even though it's in a weird order and includes a bunch of other terms, it includes all of the terms a sub 1 up through a sub big N. And the sum of those terms is precisely s sub big N, and so those all cancel out, and left in that difference is a bunch of terms from the sequence A, whose indices are all greater than or equal to big N. So we could take, say, k to be the maximum index amongst those terms, and then those terms would have to be a subset of the set of terms a sub big N plus 1 up to a sub k, and so their sum, that difference, in absolute value is less than or equal to the absolute value of each of those terms by the triangle inequality, which is less than or equal to the sum, the absolute value of a sub n plus 1 up through the absolute value of a sub k, which we've already argued is less than epsilon over 2, because all these indices are beyond big N2. The final step is to tie the two connections together, both being less than epsilon over 2 apart, which will force the total difference to be less than epsilon. For all n greater than or equal to big M, the absolute value of t sub n minus a is equal to the absolute value of t sub n minus s sub big N plus s sub big N minus a, is less than or equal to, by the triangle inequality, the absolute value of t sub n minus s sub big N plus the absolute value of s sub big N minus a, is less than epsilon over 2 plus epsilon over 2, which equals epsilon. So the sequence of partial sums t sub n converges to a, and thus the series b sub n converges to a as well. This theorem has nice implications for absolutely convergent series. We can rearrange the terms and not be concerned about the sum changing. But what if we don't have that absolute convergence? What if we just have a conditionally convergent series? We've already seen that our classic conditionally convergent series, the alternating harmonic series, can sum to multiple different values. And a natural question that might follow are, what are the different real numbers that could act as a sum for this alternating harmonic series? And remarkably, it's any real number. There is some rearrangement of the alternating harmonic series that adds up to 1,000,000, or to pi, or to whatever real number you want. And that's actually true for any conditionally convergent series. This is the statement of the Riemann Rearrangement Theorem. Let sum of an be a conditionally convergent series and let L be a real number. Then there exists a rearrangement of the series converging to L. To prove this, let's define two related sequences. Let's define an plus to equal an if an is greater than or equal to 0, and to equal 0 if an is less than 0. So we're basically saying keep all of the positive terms and replace all the negative terms with zeros. And let's define an minus to be equal to an if an is less than or equal to 0, and equal to 0 if an is greater than 0. So this is the new sequence formed by just keeping all the negative terms and replacing all of the positive terms with zeros. Since the series an is conditionally convergent, the series an plus and the series an minus are both divergent. This statement might warrant some additional justification, so I'd encourage you to think about how you might prove this is true. The general idea for making a rearrangement that converges to L is to take positive terms from our series until we first exceed L, and then take negative terms from our series until we first become less than L, and then take positive terms from the series again until we exceed L, honing in on that value. So let P1 be the smallest positive integer, such that the sum of the first P1 terms from A plus become greater than L. And we know this has to happen eventually, because the series A plus has entirely non-negative terms and it diverges, so it diverges to infinity. It's unbounded. And now let's let Q1 be the smallest positive integer, such that L is greater than, and let's start using summation notation here instead of the dots. the sum n equals 1 to p1 of a sub n plus the sum of n equals 1 to q1 of a sub n minus. And we know such a q1 exists because all of the terms a sub n minus are non-positive, and so their series must be diverging to negative infinity. And then we let p2 be the smallest integer larger than p1, such that the sum n equals 1 to p2 of a sub n plus the sum n equals 1 to q1 of a n minus is greater than L. And we continue with this back and forth, defining q2 and then p3 similarly. And we can view the resulting sums in this process as partial sums of a new series whose terms come from the sequence a1 plus up through ap1 plus, and then a1 minus up through aq1 minus, and then ap1 plus 1 plus up through ap2 plus, and then aq1 plus 1 minus up through aq2 minus, etc., etc. Let's let S sub k denote the sum of the first k terms from this sequence. And if we consider the series whose terms come from this sequence, it's not quite a rearrangement of the original series because it has a bunch of extra zeros, but it has all of the non-zero terms exactly once, and so it will converge to the same value as some rearrangement of the original series. So we just need to show that the series with these terms converges to L. That is to say that the sequence of partial sums whose terms come from this list converges to L. And that's going to be a consequence of the fact that we chose each pi and qi to be the first index, for which adding the term a sub that index, positive or negative, brings us above or below L. So let's think about the positive case and write down an inequality. We've been alternating back and forth between adding positive terms until we first become above L, and then adding negative terms until we first become below L. And let's say we're on the ith step of this process. So the term a sub pi plus will be what we've just added to become above the limit L, and then we added negative terms until we add on a sub qi minus, and then adding terms in the I plus first step. The index p sub I plus 1 will first bring us beyond the limit L. And so I can write this inequality on the right-hand side that L is less than the sum of all the a plus terms from an index of 1 all the way up to p sub I plus 1, plus the sum of all the a minus terms from an index of 1 up to qi. But I can also add an inequality on the left-hand side of L, because since the index p sub I plus 1 was the first term that made us greater than L, if we just write this whole sum without that last term added on, it has to be less than or equal to L. So we can fill this in on the left-hand side. This is the same expression on the right, just missing that final term, and so we only have the index in the first sum go up to p sub I plus 1 minus 1. Subtracting the left-hand side from all three sides of this inequality leaves us with 0 on the left, with this difference in the middle, and just with the single term a sub pi plus 1 on the right, because all the other terms cancel out. And currently that partial sum in the middle is the one with index pi plus 1 minus 1 plus qi, but I'd rather have a statement about the partial sum with index pi plus 1 plus qi, because that'll correspond to one of the points that's furthest out, one of the points that occurs right before we change direction and start subtracting things. So to obtain an expression involving the difference between that partial sum and our limit, let's negate all three sides, reversing the direction of the inequality, and then add on a sub pi plus 1 plus to all three sides, leaving us with this statement. We again have the difference between m and a partial sum bounded between 0 and a sub pi, but this time the middle is the partial sum with index pi plus qi. And this is true for all I. Since the an tend towards 0, the difference between these partial sums and our limit can be made arbitrarily small. So the subsequence of partial sums of this form, the ones whose index can be expressed as pi plus 1 plus qi for some I in the naturals, converges to L. That inequality we wrote down was based on adding a term that first made us greater than L, and you could write down a similar inequality that corresponds to adding a negative term to first become below L. And this would allow you to argue for this inequality, stating that the difference, L minus a partial sum whose index has the form pi plus 1 plus qi plus 1, is bounded between 0 and a sub qi plus 1 minus. And what makes this argument so confusing is all of the notation and all of the indices. But the actual concept behind it is relatively intuitive. If your sum is greater than the limit, and you take some step down, and now you're less than the limit, your difference from the limit can't be any greater than that step size. And those step sizes are tending towards 0. So the subsequence of partial sums of this form also converges to L. Now just having two subsequences of our partial sum sequence that converge to L, generally speaking, wouldn't be enough. to show that that whole sequence of partial sums converges to L. But these two aren't just any subsequences. They each represent the furthest point we reach on a number line before we start moving in the opposite direction. In other words, for a fixed I, for any index k in between pi plus qi and pi plus 1 plus qi, we have that the partial sum sk is bounded between the partial sums for each of these indices. And if we have an index k that's in between pi plus 1 plus qi and pi plus 1 plus qi plus 1, then our partial sum sk is bounded between the partial sums with these indices, this time in the opposite direction, because the values of our partial sums are decreasing as we progress from an index of pi plus 1 plus qi up to the index pi plus 1 plus qi plus 1. So in either case, we get this bound. And so for any epsilon greater than 0, there exists a point far enough out in both of those subsequences that they're within epsilon of L. And since sk lies between terms from these subsequences, it must also be within epsilon of L for values of k past this index. And this covers every partial sum. And so we get that the total sequence sk converges to L. And like we said before, the sum of these terms isn't exactly a rearrangement of our original series, but all it has is extra zeros, and so it converges to the same thing as a rearrangement, and we've forced it to converge to L, proving our theorem that for any real number L and conditionally convergent series an, there exists a rearrangement of an converging to L. Now this proof was kind of challenging. I wanted to go through the proof because I think it's such a fascinating result. But there's not much that will build upon this. So if you didn't track with every detail, I would say that getting the gist of the proof and getting some exposure to a more complicated proof is worthwhile enough, and you'll still be able to track with the upcoming content. Moving forward, we have a little bit more to discuss about series, and then we'll change gears and move in a different direction, exploring the basic topology of the real number line.